Applications of differential calculus, page 8. First thing on page 7, maybe your copy of the problem set doesn't have this last sentence on it, which is important. It tells you what exactly you're supposed to do. A manufacturing company makes door hinges. This is another factory problem. With factory problems, they're all about what is the optimum number of widgets they should make every month to make the most money. Okay, so in this case, they say that they can make between 50 and 150 per hour. No use making more than 150. They can't sell it. Okay, and they do have a minimum of 50 that they can make because they always have somebody to buy those first 50. It's called the standing order. The cost function for making X hinges per hour is this function here. And of course, it's valid between 50 and 150. And they're saying, find the minimum and maximum hourly costs. When is C maximum, when is C minimum? And say what the value is for the production level, which would be X, the number of hinges you make, when each occurs. Okay, so of course, we're going to take the derivative. The derivative of the C function is 0.0007 times 3 times x squared. We use the power rule. 0.1796. We use the power rule again. 2x plus 14. Is that 14.663? And then no x because it went away when you take the derivative. So that's the first derivative. We probably want to take the second derivative also because the second derivative is going to tell you if it's a maximum or minimum, and they're already asking that. So to get the second derivative, we have 0.0007 times 6 times x minus 0.1796 times 2, and that's it. Okay, so let's simplify each one. For example, 0.0007 times 3 would be 0.0021 x squared minus 0.1796 times 2 is 0.1796 times 2 is 0.3592 x plus 14.663. And to find the maximum and minimum points, all we need to do is set it equal to 0. And this is a parabola, as you can see. It's an x squared function. So we're not going to find more than one stationary point. But let's see what the stationary point is. There's a couple ways we could do that. One is we could graph it, and the other is we could use poly-SMLT. And let's see. Let's try poly-SMLT this time. Sometimes with these big numbers, poly-SMLT is easier because you don't have to like sit there zooming out and things like that. So let's go to poly-SMLT poly-root finder, and then we're going to say it's a second order equation. And then we're going to put in the numbers here. We're going to put 0.0021 for A2, negative 0.3592 for A1, and 14.663 for A0. So I'm going to put those in. Just pause for a second here. Okay, so I put in the value of A2, A1, and A0, and then I press solve. And it gives me two numbers. And it gives me one of them in fraction form. Let's see if I can take it out of fraction form. See, it's in fraction form here. I don't want fraction form. Decimal. Okay, now solve. Okay, so one of the numbers is 103.7. The other one is 67.3. Oh, I'm sorry. These are the 0. I'm sorry. I said that there would only be one 0 point, but actually, of course, there's 2 because it's the x-intercept. I was thinking vertex, but I was wrong. Sorry. So the x values which make this true would be 103.7 and 67.3. So probably one of these is a minimum and the other one is a maximum, but we'll find out. Let's do the second derivative. And let's simplify this. It's going to be 0.0042x, and then minus 0.1796 times 2, which is minus 0.3592. Okay, so when is that equal to 0? This is equal to 0. Let's see, 0.3592 divided by 0.0042. Okay, so 3592 divided by 0042. So we get 85.5. So let's draw a sign diagram for both. So in one of them we have 67 and 103, and the big positive number gives us a positive, and this big negative number gives us a positive, and in between we're going to have a negative. And then that's for the first derivative. The second derivative, at 85, we're going to have the inflection point. And then for big positive numbers, we're going to have positive, and big negative numbers, we're going to have negative. So you can see that the 67.3 is going to be a maximum, because you see it's concave down at that point. So this is a maximum. And the 103.7 is going to be a minimum, because it's concave up. Okay, oops. Oh my gosh. Okay, so that one's going to be a minimum. So that we found the minimum and maximum and the production levels for each course. The production levels for each. Okay, so the x. So for maximum, the x is going to equal 67, and for the minimum, the x is going to be 104. Okay. And then we can also check the cost for each one, because to actually find the maximum minimum, we should also check the endpoints, right? 150 and 50. So maybe the best way to do that is we could graph the C function, and then we could see if the endpoints might be bigger than that. Okay, so I'm going to put that in for y equals. So first I'm going to get out of polynomial. Then I'm going to go y equals, and now I'm going to plug in this equation here, that equation there. So bear with me while I do that. Okay, I've almost got it typed in. There we go. And now let's go back and check what I put in here. 14.1796x squared. Okay, I think it looks good. Now I'm going to graph it, and I will need to adjust the window. Luckily, they give me this range, or the domain between 50 and 150. So I'm going to put that in for x min and x max. So x min is going to be 50, and the x max is going to be 150. Sometimes it's really helpful, the fact that they give us a domain like that. Okay, so I'm going to just do a zoom fit, and it'll blow it up a little bit more. Okay. Alright, so it looks like, let me check that. Oh look, I only put x squared, it should be x cubed. I thought that was weird. It shouldn't be a quadratic. X cubed. Alright, now let's try again. And now it's probably going to be off the screen, and we're going to have to adjust the zoom. So let's do zoom fit again. And then we're going to graph again. Alright, now it's graphing itself. Okay, Oh, interesting. Okay, so let's see. Let's do a trace. And remember how we have two functions? We have a local max, which is 67. 67. I can't even see it. 67. So it's going to be about there. So it's about, it's the, do you see the cost function goes up to about 546? Okay. So that is a maximum, but it's a local maximum, right? Well, look at that. What about that? Doesn't that look like it would be the real maximum? Okay. What about the minimum? The minimum is supposed to be at 104. So let's go to 104. 104, yeah, that looks like a minimum, all right. There we go. It's about there. It's about 529. Okay. And then, so let's go all the way to the top. Look at that. The most expensive it can get is if you go to x equals 150. Then it's $680.95. So that's the end point. And we also need to check the end point to see what the end point cost is, right? So actually the max is going to be, this is a local max here. This is the local min. So actually the global max is going to be x equals 150, and the y value, which is the cost, is going to be 680.95. 680.95. And what would be the global min? So the global min would either be the local min, or we need to check the other endpoint, which would be 0. So let's check the 0 endpoint. Oops. Well, let's check the 50 endpoint, actually. The 50 endpoint. So we'll do trace, 50, and the value is 531.65. So let's see if that's it. 531.65. Now we need to check the value at the local min, which is 104. Oops, 104, not 101. 529.80. It's a little bit lower, okay? So the global minimum, even though we check the endpoint, the left endpoint, the local minimum, which is x equals 104, and the cost is equal to 529.80. That's a lower value. Okay? So those are that's the global max and the min. 150, 680, and 104, 529.80. All right. That was 7. Phew. Okay, 9. A manufacturer of electric kettles performs a cost control study. They discover that to produce X kettles a day, again a factory problem, the cost per kettle is given by. Now remember, this cost is the cost per kettle, so it needs to be multiplied by the number of kettles to find out the total cost. Okay. With a minimum production capacity of 10 kettles per day, how many kettles should be manufactured to keep the cost per kettle to a minimum? Okay. All right, so let's see. We have a cost function. Of course, we want to take the derivative to see when the smallest, when it's a minimum. So the derivative of log is 1 over x. The derivative of this, well, it's a power, so we're going to do the power rule. So 2. And then we got to take the chain rule. So the chain rule of the inside of here would be -1, but then don't forget the 10 here. So actually it would be -1/10. And I made that mistake about 2 minutes ago, so be careful. All right, and then let's multiply this out. So we'll have 4 over x plus 2, 30 minus x over 100. And let's set that equal to 0 because we're looking for the stationary points. And then we'll multiply by 100x to get the 100 and the x out of the denominator. So then we'll have 400 plus negative 2x times 30 minus x equals 0. Now we'll multiply this out. We'll have 400 minus 60x plus 2x squared equals 0. And then we could find the roots of this. When would this equal, what x's would make this equal 0? Let's use poly-SMLT instead of doing the quadratic equation. Poly root finder, order 2, and then we're going to put 2 in for x for a2. We're going to put negative 60 in for a1, and we're going to put 400 in for a0. And then we're going to solve, and we'll get two roots, 20 and 10. Okay. And so now we're interested in seeing which one of these roots is a minimum. So let's see, we could graph it, or we could take the second derivative. Let's take the second derivative. Okay, so the second derivative of this function here, oh my god, maybe this is a bad idea. So it's going to be negative 4 over x squared, and then the negative 2 over 100 times 30, and then we're going to have negative 2 over 100. Oh, actually, this is just going to go to 0 because when you take the derivative of this, it becomes 0. And then the derivative of negative 2 over 100 times x is just going to be negative 2 over, it's going to be plus 2 over 100. Okay. So our function, let's see, when is the inflection point for this one? It's going to be 4x squared equals 2 over 100. And so it's going to be x squared equals 4 divided by 2 times 100. X squared equals, okay, so that's 400 divided by 2 times 100, which is 200. 200. And so x is equal to 10 square root of 2. Okay. Which is about 14.4. 14.1, something like that. Okay, so, and then if you put a big positive number in for C dash dash, you're going to get a really small negative number here. It's going to be positive. And then if you put a really small, if you put a big negative number in, you're going to get also a very small negative number. You get a positive number also. Okay, so this is a it's concave up, or concave, yeah, concave up in both cases. So that means both 10 and 20 are going to be like minimums. So we better graph this to see what it looks like. Should just graphed it from the beginning, right? Okay, so it's going to be 4 log x plus 30 minus x squared divided by 100. And then, so let's graph this. And we're going to get this function here. And let's see, what are the values for 10? It's going to be 13.2. And what are the values for 20? 20. 12.98. Okay. So, and like I can't, let's try to zoom in a little bit here. We'll do a window, and I'm just going to make the Y max like 40. See if we get a better picture here. Still a mystery. Oops. So we'll do trace 10. That gives us 13.2. And then we do trace 20. Get 12.9. I still can't see what's going on here, so let's make the window a little bit narrower. This is 10 to 150, we'll do 10 to like 30. Then we'll graph. It kind of goes down, you see. Okay, so the 20 is going to be the lower minimum. Okay, so how many kettles should be manufactured to keep the cost to a minimum? It should be 20. Okay, we can see on the graph the 20 is a little bit lower than the 10. Alright. By the way, I regraphed this, and so this is like x equals 10, and this is x equals 20. You can see that 20 is slightly lower than 10. So both are stationary points, but this one is a local minimum. Okay? Alright. 11. Consider the manufacture of cylindrical tin cans of 1 liter capacity where the cost of material used is to be minimized. This means that the surface area must be as small as possible. Explain why the height h is given by h equals 1,000 pi r squared centimeters. So basically, let's first write an equation. They want to minimize the area of the surface area of the cylinder. And remember that a cylinder has 3 pieces. It's got a lid, it's got the bottom, and it's got the sides. Looks kind of like that. So the dimensions of each one of these, or the area of each one of these, this one's going to be pi r squared. This one's going to be pi r squared. And this one, this rectangular piece, is going to be 2 pi r h. And if you add all of these together, then you're going to get the total area. So let's add it all up. 2 pi r squared, surface area equals 2 pi r squared, plus 2 pi r h. Now remember that the volume of the cylinder is going to be 1 liter. So we could also write another constraint equation, which would be that the volume, which is pi r squared times h, is going to be equal to 1. So, or 1,000 in terms of centimeter cubed, 1,000 centimeter cubed. So now we could say that h is equal to 1,000 centimeter cubed divided by pi r squared centimeters squared. So that's centimeters, right? Okay, so that was part A. Part B says, show the total surface area A is given by this, and so we're halfway there. Now we're going to take the h expression here and we're going to put it in for this h, and we're going to get 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. And then we're going to cancel the pi's and we're going to cancel that. And now we have 2 pi r squared plus 2,000 divided by r. Did we get what we wanted? Yes, we did. Okay, now it says use technology to help you sketch the graph of A against R. So we're going to put this equation we're going to put in the calculator. And we're going to graph it. Let's see, y equals, and then we're going to put this in 2 pi r squared 2, pi r, instead of r we're going to put x because the calculator only has x. 2 pi r squared plus 2,000 divided by x. Okay, so we've graphed A against R, that's what it looks like. Now find the value of R which makes A as small as possible. I'm just going to draw a sketch of this graph here. Okay. Use technology. Okay, we just did that. Find the value of r, which makes a as small as possible. So it looks like it's this point here, right? So now I'm assuming they're allowing us to use technology again. So let's use the second calc minimum function. And then we're going to figure out what is the value of this one here. Okay, so that's the left bound, and then we go to the right bound. And enter. And so the minimum is 5.42. So the x, or the r, is equal to 5.42. And the y, which is the surface area, is going to be equal to 553.6. Okay, and so that is, so we found the value of r, which makes a as small as possible. Sketch the can of smallest surface area. So that would be like this can here, except the r is going to be 5.42 centimeters, and the h is going to be 1,000 divided by pi times 5.42 squared, which is 1,000 divided by, 1,000 divided by pi 5.42 squared, and that'll give us 10.8. The height is 10.8. Okay, so they just wanted to sketch the can with the dimensions. That's it.